I don't think most high school classes really do computer science in a real way, so perhaps that's not surprising. But, okay, well, if you take a real CS class or if you take MIT 600 online, you will learn this, I guarantee you. And to remind you of the notation we'll use, we defined this thing about limits at infinity. So as x goes to infinity, we say a function f of x approaches L if, for a given epsilon, you can find a big number n, so that whenever x is bigger than that big number n, then f of x will be close to epsilon. So pictorially, you think of this as, some function which, as x gets very big, it tends close to some limit L, like an asymptote. So if you want to make the function within, say, some epsilon of that limit, you just need to make sure x is bigger than n. So whenever you get bigger than n, you're going to be close to L. That was the definition of limits at infinity we used. So here's how computer scientists use this. Suppose you write a program, you write a computer program in Python or your favorite language, and it takes an input. So maybe it takes a list with some length, or a number which size is measured by some number of digits or whatever. Any input whose size is measured by a number x. And I should have capitalized this. You assume the program will take longer to run when the input is larger. Pretty natural. If you're sorting a list, longer lists take longer to sort. So if you assume the function takes longer to run for larger inputs, we can define a function. So this is the timing function, t of x, which is the function given an input x, how long does it take the program to run? Perfectly good function. For every input, there's one output t of x, even if I have no idea what that is. This is a perfectly good function. So, in computer science, the central question you ask in complexity theory is, how does this timing function change as the input gets larger? Right? If I want to sort a list and I double the length of the list, how much longer will my sorting algorithm take to run? Questions on this, or does that question about timing make sense?
I have no questions or comments or anything.
Okay. Hopefully a very natural, useful question, especially if you're going to do high.
Now that I think of it, I do have a question.
Oh, good.
What kind of programs wouldn't have a just f of x equals x?
Most of them.
Complexity. Oh, okay.
Linear functions are very uncommon. Most functions have something other than x. So for instance, a function which retrieves from a dictionary in Python. So you have my dictionary, and then you want to look up a function which just retrieves from your dictionary a key. So you might think, if I have some dictionary and I look up a key, this is obviously going to get longer if my dictionary is longer. But that's not true. Python is very well optimized, so this function, which simply looks up in your dictionary a key and outputs the value, this has a time complexity called O of 1, which is constant time. That's very impressive. No matter how long your dictionary is, it still takes a constant amount of time to look up the key and return the value. I'm cheating a little bit. This is something called amortized constant time, which means on average, across many lookups, it will be constant. But that's still quite impressive, because you would think that it should, like you say, you would think it should be like f of x scales like x. If you double the length of the dictionary, it should take twice as long to retrieve the key, because you have to go longer into the dictionary to find it. Not true. This is called caching. So you will sometimes hear me make jokes on Slack when I say, oh, you have O1 access to that in your head. I'm making a joke saying, you have optimized your brain to retrieve this piece of information in constant time. Like if I say you can find hentai maid porn in O1, that means you've optimized your head with caching so that you can retrieve the hentai porn in constant time rather than linear time. Good question. Does that make sense?
I'm just gonna be here laughing. I was at first when you said constant time, I was like, oh wait, an infinitely long dictionary. That's a good idea.
Yeah, I mean, you You can make the dictionary fill up your whole hard drive, and still amortized across many lookups, it will still be constant, which is impressive.
Jesus.
Yeah, I
That's
mean,
pretty good.
I've exploited this many times. It's a very useful feature of Python. Good. Other questions about lookup or big O?
Or wait, or are they just faking it by making the quick lookups take longer?
Oh, right. Well, yeah, I mean, you would never want to increase the complexity of your program. I mean, if they could get a smaller constant, they would, right? So they're not averaging it by making the long ones take shorter and the short ones take longer. They're trying to make all of them as short as possible. It just so happens that in making them all as short as possible, they happen to have made it, on average, to be approximately constant. I have to tell you what this big O means. This doesn't actually mean it's the same number for every lookup. It just means this is upper bounded in a particular sense by a constant. So it's not the same for every lookup, it's just that it doesn't grow linearly with the length of the list.
Okay.
Good, let me make that more precise. So I claimed that this is where limits are useful. So if you ever take a course in algorithms or theoretical computer science in undergrad, you will see these definitions and you will prove things about them. I will not do that here, I'll just tell you what they are. So the most common ways of measuring complexity are big O and little o. Big O is more common, it's also harder to understand, but I'll do that first. So remember, t of x was the function that tells you how long it takes your program to run. Input of size x. So the notation t of x equals big O of f of x. I'm defining this entire expression as a Boolean, the same way we defined a limit. I'm defining this expression, t is big O of f, means there exists a real number m, so that if you take the limit as n goes to infinity of the supremum of the set of all ratios, t of x over f of x, where x is greater than n, then that limit exists and it's equal to m. So roughly speaking, it's hard to understand this. This expression is sometimes called lim sup for obvious reasons, because it has a limit and a supremum. If you take an advanced math class, you will learn more about lim sup. I will not tell you about this. But what this roughly means is that as the size of the input gets very large, there's some function f of x which you're using as a comparison in your big O, some f of x, and there's the function for the actual program that you're interested in, which might oscillate a lot, so it wiggles a lot. Here's t of x. But the claim is that as you get very large, the function you're interested in divided by the comparison function f, although it can wiggle, it's not going to settle down to some constant number, it's always going to wiggle. The wiggles will always be smaller than some upper bound. So the ratio dividing by t of x over f of x, this is always upper bounded by some number, say 3 or something. It never, even if it wiggles, the ratio is never going to exceed 3 for very long. That's what we mean by lim sup. So roughly speaking, this is saying the time it takes your function to run approximately for large input is going to act like a constant times your comparison function f. That's what we mean. So very often people say, okay, searching a list of length n is big O of n. Why do we say that? Well, if you have a list with n elements and you ask the question, is 5 in my list? To tell whether the integer 5 is in your list, you have to look at every single element and check whether it's 5. So if you make the list twice as long, you have to look at twice as many elements, typically. So the time it takes you to search the list will double. So that function of searching a list is big O of n. I should hedge that this is on classical computers. Classical. On a quantum computer, you can actually get square root of n, which is very surprising. You can get big O of root n, which is weird. You double the length of the list and you don't even have to look at twice as many elements. You only have to look at square root of 2 as many, which is very weird. So that's big O. Small o is a stronger bound. We say the function is small o, little o, of f if the limit as the input goes to infinity of your time function divided by f goes to 0. That's very different. It's not a constant. It goes to 0. This is saying as you get a large input, t of x gets much smaller than f of x. So this ratio goes to 0. So roughly speaking, this says f of x is an upper bound, a strict upper bound, for the time it takes your program to run. T of x grows much more slowly than f of x. So big O is roughly a constant proportionality, small o is roughly a strict upper bound. Good. Questions or thoughts on this?
I have a question. How can I write big O in LaTeX?
It is slash...
LaTeX.
Did you really say LaTeX or latex? MathCal O. We use MathCalographic of O, so MathCal O. So MathCal O of n, for instance, is linear time.
Okay. That'll come into use later.
You'll probably be making jokes about O1 hentai lookups soon. Other questions?
I have no questions.
When I was at Domeyard, my one coworker, I would always react very quickly with emojis on Slack, and he would say, "You have O1 lookup to Slack emojis for some reason," which is still true, I think, on our Slack. Okay, just a quick plot. Here is how quickly a function's timing, or a Python function's timing function, t of x, would grow for different big O. So down here, whoops, here's O of 1, which is, say, lookup in a cache, like a dictionary. Cache lookup is O1. N is like, for instance, searching a list. On a classical computer, as you see, searching a list. Almost all efficient sorting algorithms like quicksort are all O of n log n, where here in computer science often log is not log base e, it's usually log base 2. 2's come up a lot. So this is sorting a list. Sorting a list is almost always n log n. There's some really shitty algorithms that are n squared or 2 to the n. You can see they grow very fast. So these are so-called exponential algorithms. You want to avoid exponential algorithms as much as possible because they take a huge amount of time for large inputs. If you can get log inputs, this is if you can get big O of log n, where n is your input, this is very good. So often dynamic programming, for instance, DP solutions will give you log complexity, which is very nice. It will be super efficient. So hopefully this just gives you some impression. I mean, you might naively think everything is going to scale linearly with its input, but that's almost never true. Searching a list is the only example I can think of. It's almost always log or n log in practical examples, or constant, or maybe a polynomial like n squared. It's usually these guys. Square root of n comes up sometimes.
Is this because intermediate programmers never actually post their work?
What do you mean by that?
Because it's either the people that are doing really good or really bad.
I think it's less about how good you are as a programmer. Like intermediate, it's not true that like intermediate programmers will tend to be O of n, right? I mean, usually you're upper bounded by just the structure of how the algorithms have to work, right? So, for instance, if you solve a Project Euler problem and you like Corbin's prime number problem. Remember the prime problem where you were iterating through, I don't know, for I in range n, you were looking through numbers to tell if they're prime, and then for each number I in that loop, you say, okay, I want to tell if I is prime, so I say for m in range I, and then basically, check if m divides I, if m divides I, to tell if I is prime. You remember this thing?
I do.
So this is real bad. This is O of n squared. You can tell it's O of n squared just because there's 2 for loops, right? You can kind of see it just obviously. As if you double n, you go through this for loop twice as many times, but for each of those you also go through this loop again. So you get a 2n and a 2n, which is roughly 4n squared. So it's order of n squared. So this is O of n squared. It's not really a question of intermediate versus advanced programmer. I mean, you could do this in linear time. It's really just a question of optimization, I think. I don't know if that's what you're asking.
I don't think I was asking anything, but I see what you're saying now.
Okay.
Wait, was I?
I mean,
Yes, I was.
I think you were asking, do we mostly see these because intermediate programmers don't post their work? So the assumption behind your question is that intermediate programmers would lie here, but we don't see it. And I was answering that saying, no, it's not that like where you fall on this plot is how good of a programmer you are. It's just that most of the time things are either going to be here or here, is my claim.
Yeah.
Okay. Good. Other stuff before we move on from Big O?
I have no questions or comments.
Excellent. Okay. More examples on using continuity then. So, as I said, we will probably go quite long, but whatever. So, last time we were talking about proving a limit exists. So to do that, we always assume epsilon is handed to you and describe how to pick an appropriate delta, so the definition is satisfied. So here I contrast between proofs that limits exist and proofs where you assume a limit exists. When you prove that a limit exists, you must assume epsilon is handed to you. You can't pick epsilon. In contrast, if you assume the limit exists, then this statement must hold for every choice of epsilon. So you can pick whatever epsilon you like, and it must be true. It's just like subset containment. If you're proving A is a subset of B, you always start by saying, suppose you hand me A, which belongs to A, and then you prove A is in B. But if you're assuming A is a subset of B, and somewhere in the proof you stumble across some A, which is an element of A, regardless of what that is, you can assume that it's in B, because this thing is given. So you can pick A in the second case, but not in the first case. It's the same thing with limits. So if you're proving a limit exists, you cannot pick epsilon. You have to assume it's handed to you and describe how to choose delta. But if you assume a limit exists, then you can take any epsilon you like. And we will use this in some of the subsequent proofs. Questions or thoughts on that distinction?
Nope.
Good. More. Here is an example. I will do a proof for you, and then there will be challenges. So the first part has nothing to do with continuity. It's just getting intuition for the definition. Here's a new definition. A subset of real numbers, a set A, subset of reals, is said to be dense. The word dense means every open interval of the reals contains a point of A. So what does that mean? So for instance, the rationals are dense in the reals because if we take any open interval, there's always guaranteed to be at least one rational in this interval. It's kind of intuitive based on what we've seen from chapter 1, right? Because there's kind of infinitely many rationals that are just kind of spread across the real line. So if you take any interval, you're guaranteed to have at least one. That's what dense means. Dense means every interval has at least one. So in the first part, we're going to prove, just to understand what dense means, we're going to prove that if A is dense, something stronger is true. Not only does every open interval contain one point of A, but every open interval contains infinitely many points of A. Infinitely many. Here's the proof. Okay. So we start with an open interval. So here's, in the picture, say xy. So suppose xy is an open interval. We're trying to prove that there are infinitely many points of A in this blue interval. All we know from the definition is that every open interval contains one point of A. So we have to use that. Here's how I will use that. Start with this interval I0. Since A is dense, there must exist some single point A0 which belongs to A in that interval. So there's one point. Now we form a new interval. Form the interval I1, which comes from just slicing this. You keep the left endpoint x, and then go to the right endpoint of A0. This is a new open interval I1. And I1 does not contain A0 because A0 is the right endpoint, and that's not included in the definition of an open interval. So A0 is not in I1. But now we apply the definition again. Dense means every open interval contains a point of A. So in particular, this open interval from x to A0 must contain a new point of the set A, some set A1 or element A1 in A. So there's another point, A1. But now you can probably see where we're going. You just repeat this definition infinitely often. So you go from x to A1, you don't include that endpoint, and then you apply the same argument again. Say A is dense, so you can always find another element A2 in A, and so on. So if you repeat this process using that every single open interval has a point of A, you can construct an infinite series of points, A0, A1, A2, A3. This goes on to infinity. So there are infinitely many of these points of A, which were all in the original interval I0. That's the proof. So the first claim is that if a set is dense in the reals, every open interval contains not only one point, but infinitely many points of A. Good. Does this proof make sense?
Yes.
Okay. Note in particular that the rationals are dense, but they are not complete. So this is related to your definition of completeness, which was incorrect, because we know that the rationals are not complete because they have holes. So you can be dense, which means every interval contains infinitely many, but still be incomplete, which means you still have holes.
Though, is the real set dense?
The real set is dense in the reals by definition, because every subset of reals contains at least one real, right?
Okay.
Yeah, that's kind of trivially true. You might ask, what about the algebraics? The algebraics are also dense in the reals. They are somehow more dense than Q. That doesn't really make sense, but there's more of the algebraics than the rationals. Okay, on to an actual continuity proof. Okay, this is actually a generalization of the rationals proof we did before. So here's the claim. If a function is continuous and it equals 0 for every input in a dense set A, then it has to be 0 for all inputs, not just in A. So I'll draw the picture. Hopefully this makes sense. Because if, just intuitively, if a set is dense, that kind of means there's infinitely many of those points spread across the entire line, right? So here's a dense set, which I'm trying to draw just by drawing a lot of vertical lines. So roughly speaking, if a function has to be 0 on all of these infinitely many points, roughly we think the only way for that to happen is if the function is 0 everywhere. Because if the function were non-zero at some point, say we tried to make the function up here to jump to 1, that shouldn't be able to work, because for it to do that continuously, it would have to have an interval where it increases to 1 and comes back down, but in that interval there would be an element of A where it's non-zero, and then we would break the assumption. So we're trying to prove that if you're 0 on a dense set, you're 0 everywhere. Here's how to do that rigorously. So, proof by contradiction. Suppose by way of contradiction that f is non-zero at some point, say f of y equals c. So y cannot be an element of the dense set A. Clearly y is not an element of A because we have assumed f of x equals 0 if x is in A. Okay, here's where we use continuity. So again, make sure you use your assumption whenever you do a proof. Since f is continuous, we've assumed it's continuous. We can pick whatever epsilon we want. We choose epsilon equals the absolute value of c over 2. Why do we do that? We're trying to find an interval where the function has to be non-zero. So by continuity, we can find a delta so that, I guess this should be y minus delta and y plus delta. We can find a delta so that all of the outputs of this function lie within c over 2 of c. So in particular, if x is within distance delta of y, all of the outputs have to be non-zero, because if you are within distance c over 2 of c, you can't hit 0. So all of the function outputs lie in this region. So the punchline is that f is non-zero in this interval from y minus delta to y plus delta. Here's where we get the contradiction. This is an open interval, right? So we've said f is non-zero by choosing our epsilon bars on this open interval. However, the set A is dense, which means every open interval contains a point of A. So if A is dense and this is an open interval, there must be some element of A which sits in this open interval. But if that's true, that means f of A is 0 by assumption, which contradicts that we said f of x must be non-zero in this interval because we picked our epsilon bars to keep it above 0. That's the contradiction. So that contradiction proves that actually the function must be 0 everywhere if it's 0 on a dense set. End proof. Okay, thoughts on this? Does the proof make sense? What do you think?
Yes, I have none.
Okay. Good. So in particular, this means if a function is 0 on the rationals, it has to be 0 everywhere, which is nice. Here's a challenge, which I will ask you to generalize that argument. So we ask something slightly different. Suppose two functions f and g are both continuous, and f equals g for every x in a dense set A. So the two functions are equal everywhere in a dense set. Think for a moment, and then how would you prove that means the two functions have to be equal everywhere? All x, not just in A.
Well, we would go about this the exact same way that we did the previous one, right?
Yeah. How would the argument go?
Well, yeah, thinking. Similar to the last argument, this would be a proof of, well, we try to contradict what we are not given, but what we... Yeah, I totally forget how proving my contradiction works. Well, just the words.
So you're saying you want to do a proof by contradiction so you negate the conclusion, right? So you're going to assume f of c is not equal to g of c for some c, right?
Yeah.
Okay. And then what do you want to do near that point c? Where so you're saying f of c and g of c are different near that c. How would we get a contradiction from this setup?
I don't know.
It sounds like you're trying to generalize the previous arguments. We're trying to show that if two continuous functions are different at this point, you're trying to show they have to be different on an interval, right? So it sounds like you want to use continuity somehow to pick epsilon bars to separate these 2 points.
Yeah, you're slowly drawing more and more information in.
Yeah. So I'll just sketch the argument, I won't write it up, but it sounds like what you're trying to do is say pick epsilon to be half the distance between these 2 guys. And then choose a delta, which is actually the minimum of those 2 deltas for these 2 guys. Choose a delta to get an interval from c minus delta to c plus delta. And then you know, since I've chosen the epsilon bars so these 2 can't overlap, then the 2 functions are different on this interval c minus delta, c plus delta, but that contradicts that they are equal on a dense set, because every open interval contains an element of the dense set. Is this roughly the idea you had in your head?
Not at all,
Ah, okay.
because I didn't have an idea.
No, that's fine. I mean, this works. I think this is what you were hinting at. There's actually a faster way to do it, though. You can use our favorite trick, which is define a new function, right? So define the difference between the 2, f minus g. Now we just use our previous result. If h is f minus g, and these 2 things are equal on a dense set, then their difference is 0 on a dense set. But we already proved in the previous example that if a function is 0 on a dense set, it has to be 0 everywhere. So you can actually do this in one step, just by defining a new function, which is kind of cute. But I like your...
So are these simple solutions supposed to make me hate myself?
No, I mean, they're supposed to give you a sudden aha moment. They take a long time. I mean, you will get used to this phenomenon that to solve a good math problem, you spend 1 hour banging your head against a wall, and then at the end you write up a 3-line solution which someone can read and understand in 10 seconds. It's just the nature of the game. Good. Is this argument clear, though? Are you happy this is true?
Yes.
Good. Alright, let's do one more on dense sets, I think. This is slightly harder, but let's see if you can sketch the argument. So now, assume that the functions aren't equal on a dense set, but one upper bounds the other on a dense set. So we have 2 functions, f of x and g of x, and on a dense set, I'm just going to draw it so that it's true everywhere, but we're only assuming it's true on a dense set. Just to make sure that they hit equality in some places. There we go. So on this dense set, it's always true that f of x is bigger than or equal to g of x on the dense set. This is true on the dense set. How do we prove this is true everywhere? It should use continuity somehow. What do you think the argument will look like?
This is just a thought. I don't think it's anything related to or useful here, but I'm thinking the limit of f of x as x approaches lower now.
Something from below, you're saying?
I'm thinking along the lines of the squeeze theorem. Just how the limit of f of x as x approaches a is less than, but no, in this case is greater than or equal to the limit of g of x as x approaches a. But this doesn't have any relevance to dense subsets, so I have no idea.
Yeah, the proof will be similar to the squeeze theorem, where you have three functions. But, well, first question, how should we start this? The proof should use the same ideas as the previous ones. So how do we prove that f is always bigger than or equal to g if there's not a dense set? So we should probably do a proof by contradiction. So what should I start by assuming?
Start by assuming that I guess g of x is less than or equal to f of x for all x. No.
Not for all x. If you negate this statement, so what's the negation of the statement f of x is greater than or equal to g of x for all x? What does it mean if this is not true for all?
Or none.
Well, not quite. It just means there exists one, right? If it's not true that f is bigger than g for all x, all we know is there exists at least one x where f is less than g, right? If it's not true for all, that means there's one where it's not true, right? That's the negation of for all. So by contradiction, there exists at least one. There exists a c, so f of c is less than g of c. That's how you negate a for all. So if there's some c, and, well, the way I've drawn it here won't make sense, but at that c, f of c is smaller than g of c. Now we should use the same strategy where we apply continuity to find an interval where this inequality is true. Right now we know that this is only true at a point c, f is smaller than g at a point. How do we use continuity to find an interval where this inequality is true?
I need a second to find my computer charger. Give me a sec.
Okay.
Alright, attempt number 2.
Have you got your charger?
I have.
Sweet. You sound kind of tired. Are you tired or just have a flat affect because you're, I don't know, sick of this shit or something?
Just thinking.
Okay.
If I could find something to set my feet on. Here we go.
So what was the question again?
So we started the proof by assuming by contradiction that there's a point, c, and at that point f of c is less than g of c. Now we're trying to use the same strategy we used in the previous problems, which is to use continuity to go from the assumption that this inequality is true at a point to the assumption that it's true on an interval. right? So remember before we usually used continuity and chose epsilon bars so that we could find an interval where this inequality is true. So if we assume f of c is less than g of c at this point, how can we use a similar strategy here to argue that f is less than g on an open interval?
So we know that it's continuous and therefore it can't be a point discontinuity. That means that there's an area where it deviates downwards. So we just need to find it so that the entirety of the area where it deviates downwards is below f of c, I believe. Well, below f of x.
Yeah, so you're saying there's no point discontinuity, so this area here where f deviates below g has to be true on an interval. Right, I agree that's true. Yeah. The way to show that explicitly is to use that continuity. So again, this is that choice of epsilon bar stuff. We know that the limit as x approaches c of f of x equals f of c, and the limit as x approaches c of g of x equals g of c. So if these limits exist, then for any epsilon, we can find deltas so that the outputs will be epsilon close when the inputs are delta close. So why don't we just pick epsilon to be half the distance between them again? Right, so pick epsilon to be half the distance between g of c and f of c. So if we pick those two epsilon, well, that single epsilon, and get the deltas, take the minimum of those deltas, then this interval using delta being the minimum of those two, this will be c minus delta and c plus delta. If we do that, then we know, just by the triangle inequality, that f of c is less than g of c on the interval c minus delta, c plus delta. Good. So how does why do we know that this is a contradiction once we know that this inequality holds on an open interval?
Here's the TV. Thinking.
Are your parents watching a movie again?
Nope, just TV.
Oh.
Okay, so I believe the case is that if for part of a dense subset, I believe the case was that if something is true for part of a dense subset, then it is true for like the entirety or something.
That's what we proved before, is that if functions are equal on a dense subset, they're equal everywhere. But here we're doing a proof by contradiction, and we got down to this line, right? So I think you can use this line that f is less than g on an interval plus the assumption that f is greater than g on a dense set. I think you can combine those with the definition of dense set to get a definition, or a contradiction.
So is it correct to say that since f of c is less than g of c on this set, then it is true for the entirety and therefore f of x is less than g of x?
It's not true on the entirety, because this is only true on an interval, right? So we know f is less than g on an interval.
Well, it's already contradicting what we know because since f of x, where x equals c, it's supposed to always be true that f of x is greater than or equal to g of x.
Not always true, just true on a dense set. That's the point. We've only assumed f of x is greater than or equal to g for every element of a dense set. So where's the contradiction? I agree you're saying there's a contradiction because we've said f is less than g on an interval and f is greater than or equal to g on a dense set. So how do we combine those two statements very explicitly to get the contradiction?
Do we have to show that this interval c minus delta, c plus delta is a subset of our dense set A?
Not a subset, but if we know there's one element of A, right? If we can show that there's a single A in A, which is also in our interval, then we'd have a contradiction, right? If there's a single element in both sets, we know f is greater than or equal to g on the dense set, and we know f is less than or equal to g on the interval. So if there's one element in both, there's the contradiction, because it can't be both greater than or equal to and less than at the same point. Does that make sense? We just need one point and not all of them?
Sure, but I don't know how to get there.
Well, what's the definition of dense set again?
Oh. Wait. So is the entirety of the real set effectively a also an element of A?
No, so R is not necessarily a subset of A. So it's not true that R is a subset.
Wait. Yeah, I didn't word that right.
Oh, sorry.
So A, it seems that A is many sets that eventually build up to BR.
A is just one set. It's not many sets.
But can we change A?
Can we?
No.
No, I think A is fixed. So there's one dense set A that we can't change. So all we know about this A, which is handed to us, so there's one fixed A, and all that we know about this A is that it's dense. So all we know about A is that every open interval of real numbers contains some point which belongs to A. That's all we know about it.
Therefore, lower A is in A, and this is an open interval, so lower A is in this thing.
Yeah, so there exists some A. There exists some A so that, right. So all we need to get our contradiction was the definition of dense. Because we've shown that f is less than g on an open interval. Dense tells us that every open interval contains a point of the dense set. So we just say, aha, by definition, there's a point of the dense set in this interval. That's the contradiction. Because if you're in the dense set, f of u is bigger than g of u. But if you are in the interval, f of u is less than g of u. And you cannot simultaneously have f be bigger than or equal to u and also f be less than u. So this is the contradiction. Sometimes people use this symbol for contradiction. Yes. So it's just the definition of dense. Every open interval.
I'm trying to think about which flag that is.
It's a very weird looking flag, whatever it is.
Wait, give me a sec. I have to Google this quick. I know it. I saw it somewhere.
If you find the flag, you should screen share, because I did not know it was a flag.
Maybe just an emblem. There we go.
Bank of Scotland. Their bank has the contradiction symbol. That's the worst choice. Oh my god. That's really funny, actually.
Anyways.
Okay, so
Oh, wait, did you just delete all that?
I did in a fit of laughter, but hopefully the steps were clear. So, contradiction, assume f is less than g, use continuity to show f is less than g on an interval, then use the definition of dense, because every open interval has a point in the dense set. That was the contradiction. Questions on this thing?
I have none.
Okay, let's do one more. I think the next one is a two-part, but if we get through that, maybe we can quit then, since it's probably getting late for you. So, continuity challenge. This will also test your understanding of the definition of function. So I will ask two questions. One, how many different functions f, how many functions f are there? And my pen got bigger than I wanted. Not something you often hear. How many functions f are there which satisfy f of x quantity squared equals x squared?
Seriously?
You don't like my Pen 15 Club joke? Good. How many functions f are there which satisfy f of x quantity squared equals x squared for all x? Then the follow-up question is how many continuous functions f are there which satisfy that same condition? So first question, think about this for a moment. How many different functions f are there such that the square of the output equals the square of the input for every input?
So I'm gonna guess, but not really with much proof behind it. Infinite.
Okay.
Well, I
Why?
could just keep coming up with them, but no, that's not quite right.
Why do you think? Why infinite? What's the reasoning?
There is no reasoning. That's my flaw.
Okay. What intuition leads you to believe there are infinitely many?
Because as long as you can put enough time into coming up with the word to explain it, it probably is a it is a function.
Well, let's.
No. I think that this is actually, there's only one.
What is the one? Let's ask a simpler question. Let's not worry about how many functions. Let's just worry about the single output. So consider one single input x and the output f of x. What must be true? What equation must, or what must be, there's only two choices, I claim. If I give you an input x and the output squared is the same as the input squared, what relationship must the input and output have?
They must be equal, so...
Not equal, there's two choices. They could be equal or what? What if the input's minus 1? I give you x equals minus 1. So f of x squared equals 1. What are the choices for
The absolute value of the input is equal to the absolute value of the output?
Yeah, so
Oh,
well,
okay.
reduce that into two equations, though. Make that more explicit for me.
Negative f of x equals x, and f of x equals x? I don't...
Yeah,
like,
this is
no.
good. I mean, a faster way to see it is just take the square root of both sides, right? Take the square root, that gives you a plus or minus. So there's two choices. F of x equals x, and f of x equals minus x, right? That's what you just said. Those are the two choices.
I accidentally said negative f of x equals negative.
Well, multiply by minus 1 and that's fine. So this has to hold for each x. Okay. So this tells us that at every single input, we get to make a choice. We either choose the output to be the same as the input or the negative of the input. So now, let's see if you can give more justification for why you think there are infinitely many functions. Why are there infinitely many functions that have this property that at every point the input is either, or sorry, the output is either the input or minus the input?
Say the question again?
I'm just asking I'm asking, do you now have more justification for your claim that there are infinitely many functions, now that we've seen this must be true for each input?
No.
Okay, let me ask a different question. What if it weren't a function on the real numbers? What if it's just a function on the integers from 1 to 10? 1, 2, 3, up to 10. 10 points. 10 points into the reals. And I tell you the same two choices are the only possibilities for each point, either f of x equals x or f of x equals minus x. How many functions are there that satisfy these properties, just on these 10 points?
Is there 10?
No,
Or
more than
perhaps
that.
20?
Let's just go one by one. What are the two choices for f of 1?
There is f of 1 equals 1 and f of 1 equals negative 1.
Good. Two choices. Good. What are the choices for f of 2?
F of 2 equals 2 and f of 2 equals negative 2.
Good. Choices for
So
f of
this
3.
goes on to 1t eventually, but f of 3 equals 3 and f of 3 equals negative.
Good. These are all independent choices. So here's one function. Pick 1, 2, 3, 4, 5 up to 10. Here's another function. Pick 1 minus 2, then pick 3, 4, 5 up to 10. Here's another function. Pick 1, 2, minus 3, 4, 5, blah, 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 up to 10. So I get to make 10 different choices, all independently, and there are two choices for each of those 10. So knowing that, how many ways can I choose one of those two choices 10 times?
Wait, what was the question again? I missed the first bit. I don't know how.
So I'm asking how many functions are there on the set of 10 integers into the reals, and you've now explained to me that the way to count those functions is just to notice that there's only two choices for the output at each of these inputs, and all of those outputs are independent. So if to count the functions, I only need to make one of two choices for each of these 10 inputs, how many ways can I choose those 10?
Right, I hope so.
Wait, what'd you say?
For just these 10, I'm pretty sure it's 20.
I think it's 2 to the power 10.
Oh.
Right?
Wait, oh! Because an input 1 could be 2. Or
No.
negative 2 or something.
No, an input 1 can only be 1 or minus 1. Right? Let's do an easier case. So f from 1, 2, 3 into the reals with the same properties. I'm just going to write all of the functions. Right? Function 1. 1, 2, 3. 1, 2, 3. That's one function. Function 2. 1, 2, 3. Minus 1, 2, 3. Okay, function 3. 1, 2, 3. 1 minus 2, 3. Okay, function.
Now I understand.
See what I'm saying? There's two choices for each of these inputs, which means you multiply the number of choices times the number of independent times you make that choice. So in this case, with 3 numbers, I choose plus 1 or minus 1, plus 2 or minus 2, plus 3 or minus 3. 3 choices, 2 choices each. 2 to the 3 means there are 8 functions. Right?
I like how it took me 2 minutes to realize that we were just dealing with, like, literally the first thing I did in the statistics book.
I'm glad you have a statistics book. But yeah, independent choices.
Had.
Past tense.
Before Mrs. Marr left.
I remember years ago, 2011, I had a long chat with her about how people should learn AP statistics in gifted. Very cool person. But, okay, so now you believe there are 2 to the 10 functions from the set 1 to 10 into the reals.
Yes.
Alright, now let's back up. Back to the functions not on the integers, but on the real numbers. So now I make one choice of plus x or minus x for each real number. There's a lot of real numbers, man. So I choose plus 1 or minus 1 for this one. Here's 1.5. I choose plus 1.5 or minus 1.5. I choose plus root 2 or minus root 2. So now, to count how many functions are there on the reals, which are either plus x or minus x at each x, I make infinitely many choices. Infinitely many choices. Just like we made 10 choices when there were 10 integers. Now I make infinitely many choices, one for each real number, of either plus x or minus x. So it should be pretty plausible that if I make those infinitely many choices of plus x or minus x at each point, that there are infinitely many functions which satisfy this equation at each point. Right, so 2 to the infinity roughly, I'll put quotes around this, equals infinity. So actually, we could be more precise. If we were doing a kind of math major style math class, I would tell you the cardinality of the set of these functions is something called LF1, which is the size of the set of subsets of real numbers, which we could prove is a larger infinity than the set of real numbers. But that's just an aside. Okay, so do you believe that if I make infinitely many choices of plus x or minus x, that there should be infinitely many functions?
Yes. So I said the right thing and I had no idea why.
Yes, well, that's fine. I mean, there is no value in saying the right thing unless you know why it's true. So now I think we know why it's true.
Cool.
Okay, last thing, then we can stop. How many continuous functions? So most of the functions we picked before are going to flip around wildly, right? Because we make infinitely many choices. So some of them are plus x, some are minus x. How many of those functions in that infinite set of functions are continuous? What do you think?
I have been talking and Jesus. I was like, why are you going to Discord? And realized when you opened your screen that I was muted.
You seem to be muting yourself a lot, man.
Because the TV is on.
Ah.
Anyways, so it would seem that the only two continue. It just looks like it. I'm gonna say this. That our options are x and negative x. And does negative x do what we're actually it does? Huh.
Yeah, so we're just looking for functions which are either plus x or minus x at each point. So is there any other way we could get a continuous function which is plus x somewhere and minus x at other places, but is still continuous? So it has to look like this function somewhere, and it has to look like this function at other places, but it has to still be continuous.
Perhaps an absolute value of x or a negative absolute value of x?
Beautiful, yes. So here's absolute value, here's negative absolute value. Now we can think, are these...
Is this once again the case if there's going to be infinite because slopes?
Sorry, I think you muted like halfway through. What was the sentence?
Is this case as well going to be that there is infinitely many continuous functions because you can change the slopes?
No, you can't change the slope because it has to be plus 1 or minus 1. Right, because this has to be y equals plus or minus x. So the slope always has to be plus 1 or minus 1. The question is just, how can we stitch together slope plus 1 and slope minus 1 in a way that it's still continuous? And the only way to stitch them together is at a point where they're both 0. Right, because the only time the line of slope 1 and the line of slope -1 cross is at the origin. So actually, these are the only 4 choices, right? So you could think of this as saying, well, there's 2 choices of slope, +1 or -1, and I can only stitch them together at the origin. So I make one choice on the left side and one choice on the right side, right? I choose slope +1 or -1 on the left, and I choose slope +1 or -1 on the right. And that's the only choice I can make. So this choice was slope +1, +1. This one was choice -1, -1. This one was choice -1, +1. And this one was choice +1, -1. And those are the only choices I can make, because I can only stitch together at 0. Right? That's the only place where I can stitch together and still be continuous. So it's only 4. Infinitely many here, only 4 here. Good. Thoughts on this?
Interesting.
Yeah, I think it's fun. I'll just show you the write-up and then we can quit. So just to emphasize why there are infinitely many. So this was the equation. F of x squared equals x squared. Just take square roots, take the square root of both sides. So f of x has to be plus or minus x at every point of x, every point x. If you don't assume continuity, there's infinitely many. To show there's infinitely many, there's more than this that I'm writing down. But I'm just going to write down some infinite set of these to show that there's infinitely many. Here's how I do that. So for each integer n, I define a function gn, which is x at the integer n, and it's minus x everywhere else. So for instance, here's g1. g1 means that it equals x at 1. So that means g of 1 equals 1. But everywhere else, it's minus x. So there's a hole and then minus x. That's one function. Here's another function, g2. Take a hole at 2, 1, 2. At 2, it's 2. Everywhere else, it's minus x. Clearly, I could do this for any number I want, g3, g4. I could even do it for non-integers like g pi. So there have to be infinitely many, because I can at least pick one for every number, right? So certainly there's infinitely many such functions if there's at least one for every number. Actually, there's more than that. You could do one for every set of integers, or every set of real numbers. You just say g2 associated to a subset A is x if the input x is in A, and minus x if x is not in A. So actually there's one such function for every subset of real numbers. And as you can probably guess, there's way more subsets of real numbers than there are of real numbers. This is just like, remember the daily challenge for finite sets, when you counted the number of subsets of a set with n elements. If a set has n elements, then there are 2 to the power n subsets. So there are infinitely many real numbers, so roughly there's 2 to the infinity of these functions. That's what I was getting at before with that sloppy notation.
Is there any point in saying 2 to the infinity if it just equals infinity?
There is if you study set theory. So right now, this symbol 2 to the infinity is meaningless to us, because we haven't defined what infinity is. When you define so-called cardinal arithmetic, which is a precise way of measuring the size of infinite sets, then 2 to the aleph 0, which is, aleph 0 is the size of infinity associated to the integers. 2 to the aleph 0 is aleph 1, which is the size of the reals. And then, well, there's a question about whether this is always true called the continuum hypothesis. But if you assume the continuum hypothesis is true, 2 to the aleph 1, which is the size of infinity of the reals, is aleph 2. So I'll put a question mark because we don't know, if the continuum hypothesis holds. But anyway, so aleph 1 is the size, the infinity, which is the size of the reals, and aleph 2 is the number of functions we're talking about. So, long-winded answer, but you ask, is there a point to writing 2 to the infinity? Right now, no, it's meaningless, but it could be made meaningful if you wanted to.
Okay.
Good, okay. Anyway, so the point is, without continuity, infinitely many. With continuity, there's only 4. Continuity is very restrictive. You can only stitch together continuous functions where they are equal, and these things are only equal at 0. So there's 4 choices. But hopefully this emphasizes that even though most of these functions, there's infinitely many functions in the first category, most of them are completely uninterpretable to humans, and you could never write them down, because they would just be plus x on some random subset of real numbers and minus x on the complement. But, okay, yes, you probably have to go to bed soonish, so we can skip the remaining slides. Oh, is your bedtime extended past 10 or something?
It's generally 10:30.
Okay.
I just like getting my shower at a normal time.
Well, we can quit now if you would like to shower and possibly work on...
4 slides can't take that long, unless it's like a 4-slide thing that needs to be done at once.
I actually forget what the other slides are. Let's see. Yeah, this is an extension. I will show you the solution rather than asking you to walk through it. So you can kind of see how this is similar to the previous question. Before it was f of x squared equals x squared, so there were only 2 choices, f of x equals plus or minus x. Now we change it a little bit and say, now you have 2 functions, f squared equals g squared, which means there are only 2 choices, f equals plus or minus g. So there's still 2 choices at each point, but now it's not necessarily plus or minus x, it's plus or minus g. And the thing we're trying to prove is that if f is never 0, f of x is never 0, which means g of x is never 0 by this equation, then either f of x equals g of x for all x, or else f of x is minus g of x for all x. Makes sense from what we saw before, because you can only stitch together 2 things which are continuous when they cross, which here they cross at 0. So here's the proof. Take square roots of this equation. Obviously from the square roots, either f equals g or f equals minus g at each point x. They could be separately some points x and some points plus and some points minus. So all we have to do is prove that it's always one or always the other, that it doesn't switch. To prove that contradiction, suppose that it's plus at one and minus at another. That shouldn't be possible, because we're saying it's always one or always the other. So we assume by way of contradiction that f of x is plus g of x at one point and minus g of x at another point. Here's where we use continuity. Define h as the product. H of x is f of x times g of x. We have proven that the product of continuous functions is continuous. F and g are continuous, so h is continuous. In particular, h is continuous on x1, x2, but the product of these 2 functions is positive at x1, because f of x1 equals g of x1, which means h of x1 equals f of x1, g of x1, but they're equal, so it's f of x1 squared. And f of x1 is never 0, so the square of a non-zero number is positive. So here it's positive. At x2, f is minus g, so h of x2 is minus f squared. And f is never 0, so minus the square of a non-zero number is negative. That's what we want, because now we can use the intermediate value theorem. This is where we're using continuity, by the way. This is the deduction which would fail if continuity were not there. So we know h is positive here and negative here. There's a number between a positive number and a negative number called 0. So by the intermediate value theorem, there must be some c in this interval such that h of c equals 0, because 0 is between the positive and negative outputs. That means the product f of c times g of c is 0, because that's what h was. But f is plus or minus g, so f times plus or minus f is 0, which means f is 0, and we assumed f is non-zero for all x. That's the contradiction. Bank of Scotland. Good. So that ends
Just-
the proof. Sorry.
Just eternally refer to that as Bank of Scotland.
I am going to now. Possibly in, like, official real proofs. Good. How did I not finish writing that? Right, so very similar to the last thing. We just... Contradictions say that they switch sign, define the product, use the intermediate value theorem. Questions on this?
I have none.
Okay, I think I can do the last one in like 5 minutes, so... Whew. Last question. Suppose f is continuous. This is important. It's 0 only at a single point. So there's only a single point on the entire line where f of x equals 0. So there's a function which hits 0 at a. And we also assume that f is positive at some point which is greater than a. So maybe there's an x1, and we say f is positive there. And it's also positive at some, I don't know, maybe x2, which is less than a. So it's positive. All we know is it's positive at 2 points, and it's 0 only at a. So I won't ask you to prove it, but what do you think intuitively? What can we say about f at all points? Is there something more general we can say besides these assumptions? Can f ever be negative in particular?
Wait, was that a question? No, it can never be. No, it can never be negative because that would involve it passing over, well, passing through 0.
Yeah, good. That's the crux of the proof. So the answer, what can be said about f, is that it's always positive for x not equal to 0, which means it's never negative. And as you say, the proof is basically going to say, well, it can't be negative, because if it were, it would have to pass through 0 at a different point other than a. And we've assumed it's only 0 at a. So it's going to fundamentally involve the intermediate value theorem. You see why this claim would be false if f were discontinuous. If f were discontinuous, it could jump down here with no problem. But we've assumed it's continuous. Good. So here's the proof. And it's the last slide. So here's the claim. This is just what I'm going to try to prove. This isn't proving anything. This is want to show. So we're going to prove it's positive everywhere off a. To prove it, suppose by contradiction it were negative at some other point besides a. So here's a. Suppose by way of contradiction that it's c, it's negative. And, I mean, c can be anywhere we want, but without loss of generality, suppose c is greater than a. So c is over here. Now, I called it x1 before, but we assumed that there's some b which was x1 before, with the property that f is positive at b. And now we form the interval b to c. So we form the interval from the point b, where f is positive, to the point c, where f is negative. So we form b to c. F is continuous everywhere, so it's certainly continuous on this interval. But we know f of b is positive and f of c is negative. So the intermediate value theorem tells us that if a function is continuous on a closed interval, and there is a fixed number between f of the left endpoint and f of the right endpoint, then the function must hit that fixed number somewhere on the interval. So that means there's a d somewhere in this open interval b to c, with the property that f of d is 0. But there's the contradiction. We've assumed that f is 0 only at a single point a. So there cannot be this other point d which gives f equals 0 at d. So there's the Bank of Scotland contradiction. Good. It's all intermediate value theorem for most of these, actually. It's one of the most powerful applications of continuity.
Okay.
Cool. Questions or thoughts on this last one?
I've none.
Good. Okay, so what did we see today? Reminder of the definition of a function, using assumptions, asymptotics and time complexity and big O and little O notation,